Hello friends, welcome to the first video of physics. So the module 1 will be starting with the module 1, that is oscillations. So oscillations basically have three parts in our syllabus. Number 1 is simple harmonic motion or SHM. Number 2 is damped vibration, and then comes the forced vibration. So now let us first start with the 1.1 part, that is simple harmonic motion. So first of all, we need to know what is oscillatory or vibratory motion. So let me write the definition for you. So as you all can see, when a particle in periodic motion moves to and fro, so that is a kind of motion, to and fro, that is back and forth motion along the same path, the motion is called an oscillatory or vibratory motion. So how we can represent that? So if we can say that a particle moves to and fro in such a way that the acceleration of the particle is always directed towards a fixed point in its path of motion and is proportional to the displacement of the particle from the fixed point at any instant. So that motion will be called as a simple harmonic motion. So this is the specific definition of SHM or simple harmonic motion. So friends, here is the definition for SHM that I have already told. If a particle moves to and fro in such a way that the acceleration of the particle is always directed towards a fixed point in its path of motion, and this point is important, it is proportional to the displacement of the particle from the fixed point at any instant. So this is how we can represent the motion of a simple harmonic particle. This is the troughs here, and this one is the crest, and this motion is an SHM. So now let us relate it mathematically. So if a particle of mass m executes SHM, and if x is the displacement of it from the equilibrium position, then if we consider f as the acceleration, we can define it from the definition, we can relate it as f equal to kx with a negative sign, since f is proportional to x. Here k is the proportionality constant. Hence, the force acting on the particle must be given as, we know that force is equal to mass into acceleration. So it implies that F will be equal to m minus k into x, that is minus mu x. Here if we consider mk as mu, it is the force constant representing the restoring force per unit displacement of particle. So it is the force constant. So this is the equation that we were looking for. So what are the few characteristics of SHM? Number 1, the motion is linear motion. The graph of it will be linear motion. Number 2, it is already defined that it will be a periodic and oscillatory motion. It is already defined in the above definition. And number 3, the restoring force on the body is proportional and oppositely directed to its displacement. That we can write as F equal to minus mkx, the formula. Since it is opposite, the minus sign is there and it is proportional to the displacement. So these are the characteristics of simple harmonic motion, or short form is the SHM. That is our first small topic. So now we will directly jump onto the equations and formulas. So now we need to learn the equations, the formation of equation and the solution of the equation here. So if the mass of the particle be m and it executes an SHM with the displacement as x at any instant from the mean position O we are considering, if we consider this as the diagram of SHM, let this be the mean position O, okay, and this be a position P, so let this be the displacement of the particle x and this be the acceleration small f, and let this extreme position from the mean position be a distance a. Let us name these 2 points A and B. So let this be the schematic diagram on which we will be defining. So this is the origin position. As you all can see, the force acting on the particle at any point P, it is a random point here in the path of the particle. It will be given as in the form of differential equation as m into d square x by dt square, that is equal to minus of mu x. So this is the differential equation that will be formed from the simple harmonic motion. So here mu, as you all know, that it is the constant of proportionality, or it is known as force constant, and negative sign is taken as the restoring force is opposite to the direction of displacement. So this equation may be written as like this. Solving it mathematically, it can be written as d square x by dt square is equal to minus mu by m into x, or we can write it as d square x by dt square equal to minus omega square x. So the value of omega, we have considered omega square as mu by m, where omega is the natural frequency. So we can write it as in terms of omega. So what the final equation becomes? It becomes d square x by dt square plus omega square x is equal to 0. So this is the equation that we are getting from the consideration we have made as simple harmonic motion. So from here we can also define the time period of SHM or the simple harmonic motion, which will be t is equal to 2 pi into root over m by mu. So this is the formula for time period. So now applying simple mathematics of differential equation, we will be solving this differential equation, that is this one. So if you multiply both sides by 2 dx by dt, so writing that, if we name this equation as equation number 1, let it be, so multiplying equation 1 by 2 dx by dt, then we'll be getting it as 2 dx dt into d squared x by dt square plus 2 dx dt into omega square x is equal to 0, or this can be written as, taking it common, d dt of dx by dt whole square plus omega square into d dt of x square. Since it is written like that, this will be equal to 0. Now if we integrate, writing that, integrating, we will be getting only this quantity, the differential quantity will be removed. So by integrating we will get dx by dt whole square plus omega square x square is equal to c. So here c is the constant of integration. So c is the constant for integration. Now the velocity d is dx by dt of the simple harmonic particle is 0 at its maximum displacement. So the velocity dx by dt will be 0 at its maximum displacement. And what is the maximum displacement? The maximum displacement is x equal to a. As you can see here, it is the extreme point, so it is the maximum displacement. So here velocity v will be 0. So we can say dx dt will be 0 here at this point. Hence we get from the above equations, that is this equation, we have reached into this equation, so we will be getting another form. So the form of the equation that we will be getting from this equation at extreme points is dx by dt whole square, that is equal to omega square into a square minus x square. Or we can also write dx dt is equal to plus minus omega into root over a square minus x square. So we are getting this form. So now if we consider only the positive value of this, so we will be getting it as dx by dt equal to omega into root over a square minus x square. So bringing this value down to of dx and multiplying omega with dt, here we will be getting, after integrating the quantity, we will be getting on, let me write that, integration, what will be getting? First let me write it at integral dx by root over a square minus x square. I think you can realize what value it's going to come from the integration, equal to omega into integration of dt, or we are getting it as 1 by root over a square minus x square integration. So it is the integration of sine inverse x by a is equal to omega, and integration of dt is t equal to omega t, plus we are taking delta as the integration constant. So we are getting this value. Or we can also write it as x by a equal to sine omega t plus delta. So what the final value comes out? If we multiply x, I'm writing it with a different color so you can understand properly. It will be x equal to a sine of omega t plus delta. So this is the solvation of the differential equation of SHM. So this formula we will be using for defining the simple harmonic motion phenomena. So friends, now let us see what the equation of velocity and acceleration comes out to be. So we know that we have derived x equal to a sine of omega t plus delta. Let me tell you, omega t is the phase and delta is the epoch value. Let me write it. Delta is the epoch value, that is the initial phase. So this is the equation of displacement, and we know that differentiating displacement once, we will get the equation of velocity. So we can write that v is equal to dx dt. So what it comes out to be, if we differentiate this, we get a omega cos of omega t plus delta. So this is the equation for velocity of an SHM. When the particle is at its mean position, so at mean position, delta will be equal to 0. The initial phase will be equal to 0. Therefore, V equal to A omega cos omega t only, and that we can write it as plus minus A omega into root over 1 minus x square by a square. Why? Since at time t equal to 0, the value of delta will also be 0. So x will be a sine omega t. That is equal to, if we write cos omega t, we will get this value of it. Now, when the particle is at the mean position of the path, for x equal to 0, we will be getting v equal to v max, and that will be equal to a omega. So that's all for the equation for velocity. Again, we know that if we differentiate velocity once, we will be getting acceleration. So if we denote f as acceleration, it will be dv dt. So we will be differentiating this equation. So it will become as a omega square sine of omega t plus delta with a minus sign. So this is the value of acceleration of an SHM. So you can again consider these conditions for an SHM, where we already know that f is equal to minus omega square x, but x is the displacement. We are getting this only, that minus omega square, and a sine omega t plus delta is x. So now let us define another quantity, that is kinetic energy. So a particle executing an SHM motion both possesses a kinetic and a potential energy at different instants, as you all know from the animations of you have seen in the internet. So the kinetic energy of particle of, if we consider the mass as m, and if it is moving with a velocity v, executing SHM must be given by, I'm writing it as kinetic energy, that is Ke equal to half mv square. This is the formula for kinetic energy. And we also know that x here is equal to a sine omega t plus delta. Therefore, we can see v will be equal to dx dt. We have the equation here, so we are directly putting it as a omega cos omega t plus delta. So that is equal to plus minus a omega into root over 1 minus x square by a square. We know that. So that is equal to plus minus omega root over a square minus x square. We are getting finally this value. So therefore, kinetic energy will be equal to half mv square. That must be equal to half into m, and in place of v we are replacing with this value, that is omega square, and if we square this value we are getting omega square, and the root will be removed, into a square minus x square. So this is the final value of kinetic energy that we can derive. Now we will be proceeding further to potential energy. So we all know that the potential energy of a vibrating particle of mass m at any instant is calculated from the total amount of work done in overcoming the restoring force through a distance x. Hence force is equal to, we can say, force is equal to minus m omega square x. That we know that force is equal to ma. So the negative sign is taken as the force is opposite to the direction of motion. I have already told you that. So the potential energy, we can write it as u or we can write it as potential energy Pe, as I have written before, Ke is equal to integration from 0 to x, that is the final position, of m omega squared x into dx. So we are getting it as half, and if we integrate this, m omega square x square. So we are getting this equation as the equation for potential energy. So let me mark it for you. So this is the equation for potential energy. So now we will be defining total energy. So especially what is the total energy of this system or the particle? It will be, we are defining it as A. So A will be Ke plus Pe, that is kinetic energy plus potential energy. So if we add both of them, we will be getting half m omega square E square. So this is the equation for total energy. Now I'll be drawing the energy distribution curve for SHM. So from the diagram we will be understanding the energy. So if this is the axis for energy and here is the displacement, this is the origin position and this is A, that the amplitude, and this is also A, the amplitude or the maximum displacement. So in this diagram, this line, the red line, represents kinetic energy. The blue line here represents potential energy, and this one, the dark green line, represents the total energy. So this is the energy distribution curve for a simple harmonic motion.